One of the common problem types that you will need to solve in any organic chemistry class is a problem that says, predict the products of the following reaction, and you're given two reactants or maybe a reactant and something over the arrow. So in this lesson, we're going to talk systematically about how to crack one of these problems. Before we start, I need to tell you something important. When solving a predict the products problem, I do not expect you to write a full-length mechanism. If you are given one of these problems on the exam, chances are you will not have time to write a full-length mechanism for it. So you need to learn how to solve these problems without writing a full-length mechanism. Mechanism problems are an important class of problems, but for those problems you are given the starting materials and the products, and you are told to write a mechanism to show how you get from point A to point B. For these problems, you have to come up with the product. Now, having some idea of how the mechanism works will help you solve these problems, but you don't have to write out all the steps in their gory detail with all the curved arrows. Okay, so let's get down to work. The first step is to identify, based on the reactants, what type of reaction is taking place. So up to this point in the course, you know about two reactions. You know about acid-base reactions and nucleophilic substitution reactions. To solve a predict the products problems, you have to be able to tell me which one is taking place from looking at the reactants. And this task is actually going to get more challenging as we move further through the course and we add more reactions to our toolbox for you to have to keep on top of. We already determined in a previous lesson how to get the products for an acid-base reaction. So the focus of this lesson will be how to come up with products for a nucleophilic substitution reaction. So the first step in solving a problem like this, once you know that it's going to be a nucleophilic substitution reaction, is to determine whether a reaction will take place at all. Because for many problems, no reaction is a possibility that you have to choose from. So to determine whether a reaction will take place, you need to consider the following. First of all, is there a good leaving group present? If there's not a good leaving group present, a nucleophilic substitution reaction cannot take place, so the answer is no reaction. Secondly, are there reaction conditions that are not consistent with either the SN1 mechanism or the SN2 mechanism? And what do I mean by this? I need to give you a couple of details to clarify what I'm saying. So if you have a large secondary alkyl halide, it's secondary, so it can't undergo an SN1 reaction, but it's too large to undergo an SN2 reaction. Therefore, this would be a case of a no reaction. If you have a tertiary alkyl halide, in which case you would expect it to go SN1, but the solvent is not polar enough, that's another case in which we would get a no reaction. And a third example is if you have a methyl or primary alkyl halide, something that you would expect to undergo SN2, but the nucleophile is not good enough. If the nucleophile that you're given is a C nucleophile, that's also going to be another case of no reaction. Now, if you've determined that a reaction takes place, the way you get the product is actually fairly simple. You just replace the leaving group with the nucleophile. This, of course, means that you have to identify the leaving group. So in this case, we have a bromide as a leaving group. We have Cn- as a nucleophile. And to get the product, we simply draw the propyl fragment. And then instead of having a Br on the end of it, it has a Cn on the end of it. In order to solve a simple problem like this, as long as you know that a reaction takes place, you don't necessarily have to decide if it's an SN1 or an SN2 reaction just to come up with a product. Because if a nucleophilic substitution reaction happens, you will get the same product whether it's going by the SN1 mechanism or the SN2 mechanism. with the important exception of the chiral alkyl halides that we'll see in a moment. If the nucleophile is neutral, you need to make sure that you draw a neutral product. In other words, carry out mentally that final proton transfer step in which you lose a hydrogen from the neutral nucleophile. So in the case of terbutyl bromide plus methanol, this will be an SN1 reaction, but again, you don't have to know that to solve the problem. What you do have to know is that since it's SN1, the nucleophile is good enough. What we're going to do is take off the leaving group and replace it with OCH3. The hydrogen from CH3OH is lost over the course of the mechanism, so it needs to not be there in the product. Finally, as I alluded to earlier, if the alkyl halide is chiral, you must decide if it's an SN1 or an SN2 mechanism. If it's an SN2 mechanism, you need to draw a single product with inversion of configuration. Okay, so here's a case of a secondary alkyl bromide. It's still a small secondary because there's no branching at the beta positions, but in this case the bromine in the starting material is coming out towards you. Again, you've got Cn minus coming in as a nucleophile, and in the product the Cn minus is going back and the hydrogen is coming out towards you. If it's an SN1 reaction, you need to draw a racemic mixture of enantiomers. Okay, so a tertiary alkyl bromide, even if you start with an enantiomerically pure compound where the bromine is coming out towards you, if you react this with water via an SN1 mechanism, you can have a product where the OH is coming out towards you and an equal amount of the product where the OH is going back away from you. Okay, this concludes our discussion of nucleophilic substitution reactions using alkyl halides as the electrophiles. In the next series of lessons, we will consider the question of whether alcohols can serve as electrophiles in nucleophilic substitution reactions, and if so, under what conditions.